So, we will take the midterm exam on May 2nd, right? So the next Monday. So, and then I will post the logistics of the midterm exam on the Blackboard today. So actually, as I mentioned, this midterm exam is the closed book exam. And then and also this is the on-site exam. So which means it's an in-person exam. So you need to show up during the exam time. And then, as I mentioned, the exam will start earlier than the regular class time. So actually, I will post some detailed logistics of the midterm exam, the Blackboard today. Okay. Okay. So in the previous, so actually, in the today's class, and then so exam will cover until the where is the okay this page of the fifth slide deck. So actually this is the chapter 4 of the textbook, but I split the slide deck so that includes the single cycle processor design, and then also the late part of the chapter 4 is the late part of the chapter 4 covers about the pipeline architecture. So the midterm exam will cover until the page number 19 of the fifth slide deck, chapter 5 of the pipelining. Okay, so I hope we can cover until this page today. Okay, so in the previous class we learned about the control unit of the single cycle process architecture. So actually, in chapter 4, we learned how to build a single cycle processor hardware. So that's the real hardware. So the processor hardware is composed of data path elements. Also, our hardware requires a control unit. It is because the data path elements have the control signals. So control signals determines the behavior of our data path element. So based on the instruction, then the single cycle processor needs to generate control signals for data path element. So in the previous class, we learned how to generate control signals. And then we also learned how to build the entire single cycle processor architecture. Okay? Then we conclude this single cycle processor architecture with the performance issues. So what is the performance issue? So as I explained, okay. So as I explained, every data path element has delays. So which means that when the input is given to this data path element, the output is generated after some delay. And then actually the clock period of this single cycle processor is determined by delay of critical path. That means the longest delay in this single cycle processor. So what is the longest delay? Load instruction, because the load instruction touches actually every data path element, including instruction memory, register file, ALU, data memory, and also the write back to register file. So it is because the load instruction accesses all data path elements, then the delay of the load instruction is the longest among all instructions. So actually the delay of the load instruction decides the clock period of this single cycle processor. T. Then as you know, this is the execution time, and then execution time is proportional to the clock period. So that means if the clock period is high, so it means that it's long, then the performance is low because the performance is inversely proportional to the execution time. So how can we solve this problem? We can solve this problem with pipelining. So in this class, we will learn about the very basic concept of pipeline architecture. Okay, so from now on, we will learn about the pipeline architecture, and it's very, very critical, very, very important in this course. Okay, so let's see what pipeline is. So this is a very famous analogy of the pipelining because, you know, the textbook of this course is a computer COD. It's called the COD, Computer Organization and Design. So actually, this textbook is very popular. So which means that every university in the world used this textbook to teach computer architecture courses. So which means that this analogy is also very famous. So let's see some analogy of the laundry process. So in Korean, sepak. So, and then we can define the required steps for this laundry process. So first step is we need to use the washing machine, sepaki, and then after wash our clothes, then we need to dry our clothes with the dryer. So we need to use the dryer, and then after that, we need to fold our clothes. So it's like folding. The next required step is folding. Then the final step for this laundry process is packing our folded clothes in the closet. Okay, so let us assume that the last required step is packing. So these are required steps for laundry process. And then, like the single cycle process architecture, then we can perform these required steps for a single cloth. Okay, so every single cloth we can perform these required steps. So which means for every cloth, so we can use our washing machine first, and then we use the dryer for the next step of the laundry process, and then we can fold our clothes, and then we can pack our clothes in the closet. Okay, so let us assume that each step takes 30 minutes, half hour. So which means that in order to complete the laundry process for single clothing, then we need to consume 2 hours for a single cloth. Okay. So and then for the next cloth, we also need to take another 2 hours, and then another 2 hours, another 2 hours. So which means that in order to perform the laundry process, for us 4 clothings, then we need to take 8 hours. Okay, so this process, actually this behavior is very similar to single cycle processor. What does that mean? For a single cycle processor, then we consume 1 clock period for every instruction. So which means that it takes 1 clock period time of 1 clock period for executing single instruction. So actually, for performing actually for executing the n instructions, which means that we require n clock cycles, okay, n clock cycles, and then the entire time for executing this n instruction is the nt, where this t is the clock period of the single cycle processor. Okay, so it's the same to uh, this some single cycle processing with for the closing. Okay, but what's the problem? So what's the problem is that so it takes very long time for executing one instruction, and it's the same to the this laundry process. So for performing a laundry process for a single cloth, then it takes very long time, so 2 hours. But if we see this some time table for the laundry process, then we can found that and this task A is performed by this washing machine. Other resources like a dryer or some folding or packing. So resources for folding or packing are also it's not used. Those resources are not used for this laundry process. So this means that this is the idle. So and then let's focus on this time period. So we are using a dryer that is the kind of hardware resource, but other resources like washing machine and then there's a folding and then closet, those resources are not used. Okay, and then it's the same to the different time frames, like this time frame and then this time frame also. What's the problem? So another observation, another issues of this single cycle processing is how the resources are wasted, right? So which means that the single cycle processor, the instruction for the single instruction need to requires the 5 steps: the instruction fetch, instruction decoding, and then execution, memory, and write back. So let us assume that the instruction is in the execution step. So when the instruction is in the execution step, so which means that the ALU is used for executing this instruction. But how during this time period are the hardware resources for instruction fetch, instruction decoding, then also memory, and then write back are not used. Why? So those hardware is in idle state. It's not used. So that is the waste of hardware resources. So which means that the hardware does nothing. So these hard data path elements do nothing during this time period. Okay. And then we don't want this situation, which means that so we invest these hardware resources, but some hardware resources are not used for a certain time period, and then we don't want this situation. So not to avoid this situation, the researchers invented the pipelining. It's called some pipeline architecture. So and then simply it is called pipelining. So what is the basic ideas of the pipelining? So this analogy also explains the pipelining of laundry process. So we can distinguish the laundry process as the 4 steps, and then in this analogy, then after 1 step, then using some idle hardware resource, then we can use this hardware resource for performing some required step for different clothes. closing. Okay, so in this example, the task A is performed. Task A is performed for washing machine, and then after 30 minutes, then this task A moves to the dryer step. So which means that this washing machine is in idle state, so it's not used. So we can use this washing machine for the another task, so another clothes. Okay. Why? During this 30-minute time period, and then this task moves to the another step for the folding. Then we can use some other resources for other tasks. Like for the task C, we can use the washing machine for the task C. Also, we can use the dryer for the task B. It's the next step for the laundry process. So with this pipelining manner, then we can complete these 4 tasks, the 4 clothing on the in 3 hours and 30 minutes, right? 3.5 hours. Okay, so then what's the speed up? So speed up is 8 divided by 3.5, so which means that it's about 2.3. So the performance is improved by more than 2 times. Okay. Then if there are many tasks, so like n tasks, then with this pipelining, so if you see this pipelining, so we can find that with the pipelining manner, every task can be executed every clock, but clock period is reduced. Okay. So with this pipeline manner, then we can reduce some required step for this task. So task is given to task can be given to this laundry process every 30 minutes. Okay, so which means that we can reduce the clock frequency to the 30 minutes for this laundry process, but in this above single cycle processing manner, then the clock period is like 2 hours. Okay, so then what's the benefit? The execution time is proportional to the clock period. So if the n is very large, and so where the n is the number of instructions or number of tasks, then the required time for this this pipeline manner is about so same to the nt, but nt becomes the t original divided by 4. So which means that the speed up is about 4 times of the original setting, so single cycle processing manner. You understand? Actually, I think this is very, very simple. So actually, we can use this pipelining manner for some our real world, such as the conveyor belt system in the factory. Okay. So with the pipelining, then we can improve the performance. Why? We can reduce the clock period, so we can improve the performance of our processor with the pipelining. Then how can you apply the pipelining for our processor design? So you need to be very familiar with these 5 steps of executing instructions, because I already explained about these 5 steps for executing instructions. So, and then that is the first problem of our homework number 3. So these are required steps: instruction fetch, instruction decoding, and execution and memory write back. And then for these steps, we need to use data path element. That means we need to use hardware components. And then, as I mentioned, each hardware component have delays, and then which means that the result of this hardware component is generated at some delay. Okay. And then let us assume that this is the delay of the each step. So this is the instruction fetch. This is the instruction decoding and execution, and then memory and write back. So for the instruction fetch, we need to use the instruction memory. So we need to access instruction memory with PC, the program counter value. So which means that during the instruction fetch stage, then we need to consider the delay of the instruction memory. Okay. So let us assume that the delay of instruction memory is 200 picosecond. So which means that the address is given, the PC is given to this instruction memory, then we can get instruction, but after 200 picosecond. So in 200 picosecond. So this is the delay delta T of the instruction memory. And then it's the same to other hardware component. Okay. And then for the instruction decoding stage, then we need to use register file for reading operands from registers, right? And then let us assume that the delay of the register file is the 100 picosecond. And then during the execution stage, we need to use the ALU. Okay. And then let us assume that the delay of the ALU is 200 picosecond. And then in the memory stage, then we need to use data memory. Then write back. We need to write data to register, to a register. Okay, so which means that we need to use the register file. So it's the DNAME. So what does that mean? These data path elements have delays. Okay. So which means that in order to perform, so in order to execute an instruction, then we need to accumulate these delays of hardware components to calculate the clock period. So, and then let's calculate some delays of the different instructions for this single-site process architecture. So, for example, if we execute load instruction, and then as I mentioned, the load instruction requires to touch every hardware component. Okay, so actually for the load instruction, so we need to require instruction fetch stage to read load instruction from the instruction memory. So we need to touch instruction memory. So we need to consider this delay, and then so like load x1, 0, x2. Okay. So if we see that this load instruction, then the load instruction requires to read data from register, like source register 1. So which means the loading instruction need to access register 5. So we need to add the delay of the register 5 also for this load instruction. And then in order to generate the address for this load instruction, then we need to use ALU, and which means that we need the delay of the ALU is accumulated also. The data memory is accessed. Then finally, the data from this data memory is written back to the register. So the load instruction need to access register file. So for this load instruction, we need to add these delays. So we require 8 picosecond for executing load instruction. So this is the longest delay actually. For the store instruction, actually the store instruction does not need to access register file, right? So actually the data is written to the data memory, and that's it. So the delay of the store instruction is 7 picosecond. How about the R format? It's a 600 picosecond. How about the BQ? So BQ just change the program counter. Okay, right. So which means that the BQ does not need to access data memory. Also, the BQ does not need to write back write back the data to register. Okay. So the delay of the branch instruction is 500 picosecond, but you cannot apply the different clock period for the different instructions. So which means that we need to apply the same clock signal for every instruction, which means we need to set the clock period as the 800 picosecond in this case. So which means that the 800 picosecond becomes the clock period of the single cycle processor. Then how can you apply the pipeline manner to this RISC-V processor? So these are required steps for executing instruction. Then we can divide each step for the individual stage of the pipeline. So which means that, so firstly, let us assume that the load instruction is in the instruction fetch stage. So which means that load instruction takes 200 picosecond in instruction memory. And then the the instruction is read from the instruction memory, then this load instruction will use the register file, which means that, oh, when the load instruction is using the register file, instruction memory is not used. Okay. So during this time period, then the next instruction, like store instruction, so next instruction can access the instruction memory. Okay. So which means that when the load instruction is in the ID stage, then store instruction, the next instruction is in the instruction fetch stage. Okay. Then the same approach can be applied to the different instructions. Okay. So we can divide the some pipeline stages as the 5 stages, like instruction fetch stage, instruction decoding stage, execution stage, memory stage, and write back stage. Then we can reduce the clock period for each stage in this example. What is the longest clock for the different stage? What is the longest delay? It's 200 picosecond, right? So the longest delay becomes the 200 picosecond. So which means that we can set the clock period as the 200 picosecond for the pipeline architecture. Okay, because this is the longest delay. So we can just compare the delay of the each step. Okay. So this is the so timing diagram of the single cycle processor, and then the pipeline architecture processor. And then, as I mentioned, for the single cycle processor, then the longest delay is the 800 picosecond for this single instruction, like load instruction. So which means that the T clock period becomes the 8 picosecond. But in the pipeline processor, then during this instruction fetch stage, this instruction, the first instruction consumes 200 picosecond, and then for the next 200 picosecond, then this first instruction is in the ID stage, like 100 picosecond for the register file, and then the next instruction can be in the instruction fetch stage. So this clock period is just 200 picosecond. So T becomes the 200 picosecond. And then, the execution time is the instruction count, CPI, and then T. The instruction count is the same. So that means that the software is the same, and then the also instruction set architecture is the same, and then compiler options are the same, and then CPI. So if there is no hazard, I did not explain about the hazard, but if there is no hazard, then CPI is the same for the pipeline architecture, because we can fetch every single instruction every cycle, like this example. So we can fetch this first load instruction during the first 200 picosecond time period, and then for the next time period, also next 200 picosecond period, then we can fetch next instruction. And also we can fetch next instruction for the next 200 picosecond time period. So which means that for every 200 picosecond, we can fetch every other instruction. So which means we can execute one instruction per clock. Okay. So CPI is 1. So clock per instruction, required clock count for one instruction. It's the same to the single cycle processor, actually. CPI is 1, then we can reduce the T by 1/4. So which means we can increase the performance by 4 times. Okay, that is the benefit of pipelining. Oh, it's very good. So, okay, so it's very good. So the pipeline, we can calculate the pipeline speed up like this. So if all stages are balanced, so balanced means that, so the longest delay for 5 steps in a single cycle processor was 8 picosecond. Okay, so balanced means that every stage occupies 160 picosecond. So which means that instruction fetch takes 160 picosecond, the instruction decoding, execution, every stage takes the same delay. Okay. So which means then we can set the clock period of the pipeline architecture as 160 picosecond, which is the 1/5 of the single clock period of the single cycle processor. So which means that the speed up of this pipeline processor is 5 times. Right. If all stages are balanced, so which means the delay of every stage is the same, and so which means that all stages are balanced. But as you can see, this example it's not easy. So it's not easy to have the balanced stages in the process architecture. This is because the different hardware components have different delays. Okay. So it's not easy. So as you can see, this example, the instruction memory has the 200 picosecond of delay, and then in register 5 has the 100 picosecond. So for this case, so we need to use the longest delay. So clock period will be longer than the longest delay of the hardware component. Okay. So in this example, we need to set the clock period as the 200 picosecond. So which means that the speed up is 5x, so 5 times, so which is less than the 5 times of speed up. So this is the maximum speed up of the 5-stage pipeline. but actual speed up is about the 4x, is 4 times. It is because the delay of data path element is not balanced. Okay. Okay. So you need know this the pipeline architecture. So and then also we need to distinguish the latency and throughput of instruction. So if we just focus on execution time of a single instruction, it's a single instruction. So can we improve the latency with the pipeline architecture? Can we improve? So let's focus on the latency of a single instruction. So can we improve the latency? No. No. This is because, so let's just see this example. What is the latency? So latency is the time gap between start time and the end time. So for a single cycle process architecture, the time gap between the start time and then the end time of a single instruction is 800 picosecond. But if you see this pipeline architecture, the time gap between the start of an instruction and the end of executing an instruction is 1000 picosecond because 5 steps. So if we just focus on the latency of a single instruction, we cannot improve the latency. So which means that we cannot decrease the latency of a single instruction. But with the pipelining architecture, we can increase the throughput. So which means that we can increase the number of executed instructions, okay, with the pipelining. So you need to understand this. With the pipelining, we cannot reduce the elapsed time for executing a single instruction. Okay, and improve the throughput of instructions with the pipelining. Okay. So if you read the this first slide, then you can find the terminology parallelism. So it's hard to pronunciate. So it's called the parallelism. So parallelism means it's very hard to translate also. So in Korean, it can be translated like 병렬화, like 병렬화. So which means that we can execute many tasks in parallel, which means that we can execute or we can perform many tasks concurrently, which is called the parallelism. Okay. So if you see that this sentence, then sentence declare that with the pipelining, we can improve performance with parallelism. Okay. Then, what kind of parallelism? So, if you see that this timing diagram, and if you just focus on this time period, like from 400 picosecond to the 600 picosecond time period, then we can observe that multiple instructions are running inside of this processor during this time period. So I define that parallelism means multiple tasks are executed or performed concurrently or in parallel. It's the same to this pipelining architecture. Many instructions like load x1, load x2, or load x3 are running inside of a processor. If we just see the behavior of this processor at this time point. Okay, so many instructions are running concurrently inside of this hardware processor. So which means that with the pipelining, we can execute, the processor can execute multiple instructions concurrently, which means that we can improve performance of this processor with parallelism. Okay, and then this parallelism is called instruction level parallelism, and then it's called the ILP. So instruction level parallelism means multiple instructions are executed in parallel. So which means multiple instructions are executed concurrently. So which means that with this instruction level parallelism, we can improve the performance of a processor. Okay, that's why the first slide declares so we can improve the parallelism, improve the performance. Okay, this is very important for the performance of a computer processor because we can improve the performance with parallelism. And then there are many different kinds of parallelism, but we are learning about the parallelism for the first time in this course. So we are learning about instruction level parallelism. So which means that many instructions are executed concurrently in a processor. But then we can improve the performance. Okay. The same theory can be applied to the different process architecture. Just remember that with the instruction level parallelism, we can improve the performance. Then, which means that if we increase the number of instructions which are executed in a processor, then we can improve the performance. Okay. So this slide explains about the simplicity of the RISC-V instruction set. So you know the RISC-V instruction set is the kind of RISC type instruction, RISC, which means that this type of instruction has the very simple format, like and then RISC-V instruction has the fixed length, like the 32-bit. So which means that the decoder, like the hardware for instruction decoding, can be simplified. So we can apply the very simple hardware for this instruction decoding. So that means if the hardware is simple, then the delay can be decreased. So which means so this slide explains that the RISC type instruction is good for the hardware implementation for instruction decoding stage, but the different instruction set, such as the x86. So x86 is the CISC type instruction, so which means that it's very complex, and then which means the instruction decoding, the decoder hardware becomes very complex. So it may take a longer time for decoding instructions. So which means that for the CISC type instruction, the decoder structure gets more complex. So it's not good for the hardware design. But RISC-V is a relatively simple. I mean, relatively. It's a relatively simple, so we can implement the simple hardware decoder for RISC-V instruction. So it's also what we need to consider about the instruction design. Okay. Okay, then let's learn about the hazard. Actually, this is very, very important concept, pipeline process architecture. But also you need to understand about the hazard in a computer system. Also, it's very, very critical for the performance of computer systems. Then, what is the definition of a hazard? So, if you find such hazard, the definition of a hazard in a encyclopedia or some dictionary, it's a dictionary, then you can find the meaning of hazard like, oh, this is the very flat surface, and then if there is some crack or some cracks under this very plain surface, and like this, then this is called hazard. Okay, so that is the meaning of a normal hazard in our real world. So it's a plain surface, and there is some crack, and then so we need to jump under this crack. So and then this is called the hazard in our real world. And what does hazard mean in the process architecture? We can understand hazard like the hazard equal events that cause waste of clock cycles. So hazard, that is the meaning of hazard. So hazard is a hazard means an event that causes waste of clock cycles. What does that mean? Until now, we assume just the assumption, one instruction can be executed per clock. Right. In a single cycle processor, which means the CPI is 1. In a single cycle processor, the CPI is 1, so which means that we consume only 1 clock cycle for executing 1 instruction. And then it's the same to the pipeline architecture, pipeline processor. Pipeline processor can fetch every instruction, every clock. Okay, so for 1 clock, the pipeline processor can fetch 1 instruction, which means that the pipeline processor can execute 1 instruction per clock. Okay, but by some reasons, pipeline processors can waste clock cycles. Okay, and then these events are called hazard. So if hazard happens in a pipeline processor, then the clocks are wasted. So which means if clocks are wasted, so execution time is the instruction count, CPI, T. If a hazard happens, so we assume that CPI is 1 for every processor, but if the hazard happens, T is the same, instruction count is the same, but CPI is increased. Why? Right? Do you understand? So we assume that 1 instruction consumes 1 cycle, 1 clock cycle. But if hazard happen by some reasons, clock cycles are wasted. So which means that some instructions require multiple clock cycles. Right. Which means CPI is increased. So, the execution time is also proportional to CPI. If the CPI is increased, then performance is decreased. That's why hazards are very critical, and it's a very important concept in pipeline process architecture. Okay, so we will learn about the hazard in the pipeline architecture, and then it's also very important. So you need to understand about the hazard. So hazard, so definition of the hazard. And then there are three types of hazard in the process architecture. So the structure hazard, data hazard, and control hazard. So let's see the definition of each different kinds of hazard. The structure hazard. So clock cycles in a processor can be wasted when the required hardware resources are busy. What does that mean? The hardware resources, hardware components have limited hardware resources, right? So for example, let us assume that the register file. The register file, our register file has two source register port, okay, RS1 and RS2. And then let us assume that some instruction, also a very weird instruction, requires three source registers, like add RS1 ID. So let us assume that add ID, RS1, RS2, RS3. So like RS1 plus RS2 plus RS3. What's the problem? This weird add requires three source registers. So, but this register file has two source register ports, which means that during one clock, this register file provides maximum two source register data. Okay, but this add instruction requires three source register data, three operands from register file. What can we handle this situation? Simple, right? It's the same to our real world. So first, first clock, then the register file provides the two source register data, and then in the next clock, the register file provides the one remaining source register data, which means this instruction consumes two clocks. Right. This kind of hazard is called structure hazard. So structure hazards are caused by lack of hardware resources. Okay, it's caused by lack of hardware resources. Okay. So this is, and then what is the data hazard? So data hazards are caused by data dependencies between instructions. What does that mean? What are data dependencies? So data is caused by data dependencies between instructions. So what does that mean? Like add x1, x2, x3, add x4, x1, x5. So if we see these instructions, So the second add requires result from the first add, like here. So what does that mean? If this result is not found, so which means that it's not completed. It's not, so this result is not found in a processor. Then this add instruction cannot use the result from the former instruction. Now this is called the data dependencies because the next instruction requires the result from the former instruction, or the execution of the next instruction is influenced by the timing of former instruction. So this is called data dependencies between instructions. And then data hazard means that the clock cycles can be wasted by this data dependency. Okay. So which means that if a clock cycles are wasted by data dependencies, then we call it as data hazard. Okay. Now what is the control hazard? So control hazard means that clock cycles are wasted because of control instructions. What are control instructions? Branches or jump. So those are control instructions, which means that the clock cycles can be wasted when the control instructions are executed. So this event is called control hazard. Okay. So let's see the detail of these different kinds of hazard in the RISC-V processor. So I already explained that the structure hazards are caused by lack of hardware resources. So which means that this is the same hardware, but same hardware is requested by multiple requests. But if this number of requests exceeds the resources in this hardware, then we need to consume another cycle. So more cycles for performing some instruction in this hardware. So this is the structure hardware. This is called structure hazard. Then can you find the structure hazard in a pipeline architecture or a single cycle processor? Actually not, because you know, how can we find it? So this is the concept of the pipeline architecture. So what is the concept of the pipeline architecture? Which means that each stage uses its own hardware resources. So which means that actually the hardware resources, the required hardware resources are separated for each stage. Then we also it means that actually when we design stages on the pipeline architecture, we just split the required hardware resources for each stage, which means that structure hazards are not observed in the pipeline architecture. Okay, we just invest the required hardware resources for executing instruction. Okay, we just build up enough hardware resources for executing one instruction. So you don't need to consider about the structure hazard in the pipeline architecture. Okay, but we can actually we can imagine just imagine. We can imagine some structure hardware structure hazard for some specific case. For example, in a single cycle processor, we use the split memory. What does it mean? It's the instruction memory and data memory. But in the software side, actually, the memory is the one large memory. That is the united memory. So which means that the instructions are also found in this united memory. Also, the data is also found in the data memory. That is the software aspect. But when we design a single cycle processor, we split instruction memory and data memory. Why? Not to avoid structure hazard. Okay, right. Not to access the memory separately. So for every instruction, we need to access instruction memory every cycle, because in order to fetch instruction, then we need to access this instruction memory with the program counter, which means that for every clock, then we need to access this instruction memory. Okay, but how about the data memory? Data memory is accessed by load and store instruction. Okay. So what's the problem? For the load instruction, if the memory is united, so if we use the united memory, like instruction memory and data memory is united in the same memory, then for the load instruction, then we first need to access the memory for fetching this instruction, and then we need to access this memory for data access, which means that we need to access memory twice for the load or store instruction. So if the memory is not split, it's not divided, then we need to consume 2 cycles for load or store instructions, right? Because the memory is accessed every cycle for fetch instruction, and then additional memory access is required for load and store instructions. That's why we split the instruction memory and data memory for this process design. So we want to avoid the structure hazard. So basically, the structure hazard are not observed in our processor design. It is because the memory is split into instruction memory and data memory. Okay. Okay. Then let's see about the data hazard. So we don't need to consider about the structure hazard in this course, but data hazard is very important. Okay. So let's see this situation. So add for this example, the add store its result on the X19 register, and then the following sub instruction requires the result from this add instruction, because the sub instruction needs the data from X19. And what's the problem? So this is the timing diagram of the pipeline architecture. So add is fetched during this time period, instruction fetch, instruction decoding here, execution here, and memory is here, and then write back is here. And then the next instruction is sub instruction, X2, X19, X3. So sub instruction should be fetched during this time period, the next clock cycle 2. Then what's the problem? When does this sub instruction read data? Sub instruction reads data in ID stage, and then add instruction write data in write back stage. What's the problem? Add instruction will write data during this time period from 800 picosecond to the 1000 picosecond. But when the sub instruction is fetched very next clock of this add instruction, so instruction fetch is here, then ID is here. The sub instruction requires data during this time period. So 400 to 600 picosecond. So this is the future. This is the past. So which means that the sub instruction cannot be executed. The sub instruction needs to wait until the result from add instruction is written back to the register file in write back stage. So I said sub instruction needs to wait. Wait means the clock is wasted. Clock is wasted. So because of data dependence between add and sub instructions, clock cycles are wasted, which is data hazard. So in a single cycle processor, data hazards are not observed. Why? In a single cycle processor, we don't need to consider about data hazard because every instruction completes its execution within one clock. So during this one clock, write back is performed. So the result of this former instruction is updated to the register file within one clock. And then after that, during the next clock period, next instruction can be executed. So we don't need to consider about data hazard in the single cycle processor, but in the pipeline processor, we need to consider data hazard. So which means that, because of this data dependency, the next instruction cannot be executed. So next instruction needs to wait some clock cycles until the required data is ready in the pipeline processor. Okay, so in this example, 2 cycles are wasted. So which means that in order to execute this sub instruction, then we need to take 3 cycles for sub instruction. You understand? That's why the CPI, GPI is increased. Then, so what's the problem? CPI is increased. So which means that the sub instruction need to wait until this data, the result of add instruction is written back to the register file. How can we solve this performance issue? We can solve this performance degradation with the data forwarding. So data forwarding means that this is the required steps for this add instruction. So different, but the double instruction requires the data from the add instruction. In this example, the register number is changed. But when at the execution stage, the result of this add instruction is calculated by ALU. Okay. So even though this result is written back to the register file in the write back stage, in a processor, processor already have the result of this add instruction after EX stage. Right. And for this sub instruction. So actually this sub instruction needs to read data from register file. But actually for this sub instruction, data should be ready before EX stage because the data is processed by ALU. You understand? In order to perform this sub instruction, it's okay that the data is ready before EX stage, okay, before ALU. So sub instruction requires data before EX stage, and then add instruction generate data after EX stage. It's just one clock gap. So which means at this point, the result of add instruction is produced. So at this point, the processor has result of this add instruction. And then when this result is required, actually, when the sub instruction is in this time period, this result is required before this ALU execution, which means that the sub instruction requires data at this point. So if we just compare the result is produced at this point, and then actually the result is required at this point. So this is the past, this is future. What does that mean? Actually, this sub instruction does not need to wait until the write back stage of the add instruction. It is because when the sub instruction requires the data from the add instruction, this data, this result already exists in the processor. It is not found in the register file, but data exists. Data exists in the pipeline processor. So this sub instruction can use this data because this is the future. So this point is after the result by add instruction is produced. You understand? So if we can deliver this result to the input of the ALU, then we don't need to, actually this sub instruction does not need to wait until the result of add instruction is written back to the register. You understand? The main concept of forwarding means that when the data is required, and then if the data is found, not in the register file, if the data is found in any location of the processor, because data is already produced, then this processor can utilize this already produced data. That is the basic concept of data forwarding. And with this data forwarding, then we can avoid the waste of clock cycles by data dependencies. Okay. So not that different instruction. It's we can modify our pipeline processor hardware. Okay. It's performed by hardware, not by instruction. But if the former instruction is the load instruction, the data is generated at the memory stage. And then in this case, and then in this example, the following sub instruction requires data from the load instruction. So what is different? In this former example, the data is produced after EX stage, and then this data is required in the EX stage of the following instruction. But this is different. The data is produced after memory stage. So in this case, the following instruction need to wait one cycle. So we cannot avoid this case. So we cannot solve the data hazard using data fold if the former instruction is load instruction. And this hazard is called load use data hazard. Okay. So for this case, the clock cycles are wasted. So the performance can be degraded. Okay. So we need to also support this control. Okay. The clock cycles are wasted. Okay. So we cannot cover until the control hazard. So I will stop here, and then in the next class, I will also explain about the control hazard, so caused by branch instruction. Okay. And then, okay, so I'll stop here, and then do you have any questions? Okay, thank you for your attention. Then see you in the next class.